right, and today our focus of discussion will be on our next functional group, alkenes. All right, we talked about alkanes. Alkanes were molecules that consisted of only carbon and hydrogen and had only what type of bond? Single bonds. So alkenes are also only carbons and hydrogens, but they have at least one carbon-carbon double bond. All right, so whereas pentane we would have represented with all carbons and hydrogens, all single bonds. Okay, that would have been our alkane. If instead we put in a carbon-carbon double bond anywhere in this molecule, so I'm going to put it on the very end here. This is no longer our alkane, but an alkene. All right, and we'll talk about how to name these here today as well, but just to kind of introduce, the first thing we're actually going to discuss is the differences between alkanes and alkenes here. Obviously, they got this double bond here. So why do we classify these as different molecules? It turns out that alkenes are way more interesting than alkanes are. For alkanes, we had that one type of reaction, our radical halogenation reaction, but that's because alkanes aren't very reactive. You have to have that super pissed off radical in order to get any sort of a reaction out of an alkane. Alkenes are very different. They're much more reactive because of this double bond right here. All right, so let's talk about the nature of that double bond for a second. Okay, so alkanes. We're going to take a look at a simple alkane, ethane. We're going to draw out the Lewis structure here. Right, ethane meaning only 2 carbons. All the rest hydrogens. Okay, so in these molecules that contain only single bonds, these bonds are what we call sigma bonds. Okay, and a sigma bond is kind of exactly what you would have in your head when you pictured a covalent bond, right? A covalent bond means that there's a pair of electrons being shared. In a sigma bond, that pair of electrons being shared is located directly between those 2 atoms that are sharing that bond, right? So my carbon-carbon single bond here, these carbon atoms are sharing this pair of electron. Where does that pair of electrons live? Directly between those 2 carbon atoms, okay? Kind of to rewind back to general chemistry, you would have talked about hybridization. These carbon atoms are what are called sp3 hybridized. All right, you can kind of just trust me on that for right now, that this is what that would look like. An sp3 hybridized carbon atom means that it's got these 4 little lobes here. These are our electron orbitals. These are like the cages that trap these electrons. And so when I bring these 2 carbon atoms close to one another, again, they're going to form a sigma bond. They're going to share a pair of electrons. All right, we got some hydrogens on there as well. But again, that shared pair of electrons, it's not a pi bond, that is mislabeled. All right, that direct overlap is what we call a sigma bond, right? So we have our carbon atoms here, and they're sharing this pair of electrons in the middle. And where is that pair of electrons located? Simply between those 2 carbon atoms. So again, kind of just like we would have in your head when you think about a covalent bond, sharing of electrons. If I'm bound to another atom, that pair of electrons we're sharing is just directly between us. Nothing crazy. All right, so again, sigma bond, that shared electron pair is between those atoms. Okay? So that pair of electrons is kind of well buried in that molecule. It's sitting there between those two carbon atoms. It's kind of hard to get to, which is again why alkanes aren't very reactive. All right? So now let's look at an alkene. And again, we're going to take a look at just a very simple 2-carbon alkene. Now I'll only have 4 hydrogens because I have that carbon-carbon double bond. Okay, so our electrons for a double bond look very different than they do for a single bond. All right, we have 2 carbon-carbon bonds here. One of them is our normal old sigma bond, exactly what we saw previously, a pair of electrons that are being shared directly between those carbon atoms. All right, but the second one is a very special kind of bond, what's called a pi bond. In a pi bond, the pair of electrons being shared sits above and below the carbon atoms. All right, so in a double bond, we have one normal old, what we call sigma bond, where the pair of electrons is sitting between those carbon atoms. But now we have this second bond, and this second bond is a special bond, what we call a pi bond. And what's so special about this bond is where the electrons live. They're no longer sitting between these two carbon atoms. They're sitting above and below those carbon atoms. All right, so this is a picture of that ethane molecule here. Let's just sort of make this a little less busy to look at first. We'll take a look at the normal sigma bonds in orange here. All right, so again, that first bond in my carbon-carbon double bond is a normal old sigma bond where that pair of electron density is sitting between those two carbon atoms. But that second bond is this super weird pi bond where that pair of electrons is not sitting between those carbon atoms. It's actually pointing out above and below those carbon atoms. All right, and this little peanut-shaped orbital here that we have in purple. And my neighboring carbon also has that same little peanut-shaped orbital, and these two overlap to form what we call our pi bond. So how the heck do we know that, right? Like common sense, of course, duh. No, absolutely not. This is very bizarre stuff that falls out of quantum mechanics. It has everything to do with electrons as waves and all this other complicated crap that comes from quantum mechanics. We're just going to trust the big brains in the physics department that these are what these orbitals look like here, okay? But why it's so important is because it helps to explain why these double bonds are so much more reactive. That pair of electrons is not tucked away between two carbon atoms. It is sitting on top and on the bottom of that molecule, very easily accessible, okay? So the bottom line here is we have these pi bonds, this pair of electrons that sits above and below our bound carbon atoms, and importantly, those pi bond electrons are very accessible, i.e. very reactive. All right, so now we're going to see this pair of electrons playing roles in these chemical reactions, and again, that's because they're really easily accessible. They're sitting directly on top or underneath that molecule. What's up?
What does the IE mean?
IE means like, for example, or and thus. Okay, cool. So we have our bond geometry that helps to explain it. The other thing that's going to be sort of help us understand why alkenes are so reactive is their geometry. Okay, let's take a look at the Lewis structure. We're going to look at a slightly larger alkene to make a point here. Put 4 carbons on there. Okay, so alkene geometry, going back to what we talked about in general chemistry, these sp2 hybridized carbons. All right, and again, those are the carbons on either side of that double bond. So if we look at our example molecule here, we're talking about this guy's sp2 and this guy's sp2. Okay, these other ones that do not have that carbon-carbon double bond, they are sp3 hybridized. All right, so again, specifically talking about these sp2 hybridized carbons, they have what's called a trigonal planar geometry. Okay, so trigonal planar, if we pick that word apart, trigonal, it's because there's 3 atoms that form a little triangle. The more important here word is the planar. It means that all those atoms sit in one plane. You could do one chop and you would hit all of those atoms. All right, so the consequence is that these molecules about these double bonds are flat. All right, so trigonal planar geometry, i.e. they are flat. Okay, so specifically we're talking about our sp2 hybridized carbons and their bound atoms. Okay, so we're going to take a look at this molecule here. And we want to know what atoms lie in the same plane. Okay, so my atoms that lie in the same plane are going to be those sp2 hybridized carbons so those 2 there, as well as all atoms that they are directly bound to. So each one of them will have 2 other bonds. These atoms that are directly bound to those sp2 hybridized carbons are all sitting in one plane, are all in this flat region of our molecule here. So our sp2 hybridized carbons and all of their directly bound atoms. Okay? This one right here, I labeled as an sp3 hybridized carbon. Why did I put that in my plane? Because it's bound directly to that sp2 hybridized carbon. Awesome. Okay. So now we're looking at Lewis structures here. Let's make sure that we can do the same thing with our bond line structures. All right, so I'm going to put down a molecule here. And you are going to highlight all of the atoms that lie in the same plane in this molecule. You don't have to. You're just going to highlight, circle your atoms that all lie in the same plane here. All right, so we're going to have 6 atoms that lie in the same plane. We have our 2 sp2 hybridized carbons, the one on either side of the double bond. All right, as well as all the atoms that are directly bound. So I have these 1, 2 carbons. What are my other 2 that I'm missing here? My implied hydrogens, exactly, right? So I can draw in my hydrogens here and here just to illustrate that all 6 of these atoms lie in the same plane, right? So if you looked at this molecule and you picked it up and you held it in 3 dimensions, you would see it's got this big flat region right here where that pi bond is, again, very easily accessible. Not only because it's geometry, not only because these things are sitting flat, but remember that pair of electrons is extending above and below that flat surface, okay? So again, all this to say that the geometry as well as the electron structure of these alkenes help to inform why they're so much more reactive than our alkanes. That pair of electrons, what we call our pi electrons, are just that much more accessible. Cool. All right, so next we're going to move to what we sort of always go to when we introduce molecules, which is nomenclature. So let's just look at an example molecule. Let's do the one that we just looked at here. 5 carbons. I lied. I'm going to stick it on the end there. All right, so we had this list of rules that we built, and the good news is that our rules don't change. Okay, step 1 is still what? What do we do for step 1? Parent chain. Okay, but what we're going to see is that this is our first what's considered to be a functional group as far as nomenclature goes. All right, we talked about alkyl halides, but we just use those chloro or fluoro or bromo substituent names. Okay, this double bond here is considered a functional group as far as nomenclature goes. So when you find your parent chain, you have to look for the longest continuous set of carbons, with the added caveat that it must contain that carbon-carbon double bond. All right, so find our parent chain. Again, that's our longest continuous set of carbons that contain that functional group. Okay, so in this case, how long is my parent chain? 5. So when I'm looking at this molecule here, I know before I do any counting that these 2 have to be in my parent chain. My parent chain has to contain that double bond. So then from there, I'm going to look for my longest continuous one. Again, this is a pretty straightforward example. All 5 of those carbons lie in my parent chain. Okay. All right, so we talked about alkanes. Have what ending? A-N-E. All right, now we got real creative with alkenes. What ending do we think they're going to have? E-N-E, right? So an alkane is A-N-E, an alkene is E-N-E. Okay. I'm going to, step 2 is our substituents. In this case, we don't have any. There's not really anything we need to add here. Okay. Step 3 is to number our parent chain. All right. And this we do have to do because I have to indicate where that double bond is in my molecule. In this case, it's located between carbons 1 and 2. I could pick it up and move it to be between carbons 2 and 3, and that's a different molecule, right? So just like how we had to specify the location of our substituents, you also have to specify the location of your functional group, all right? So number 1, 2, 3, 4, 5, or I can go the other way, 1, 2, 3, 4, 5. Which one of these is going to be the correct numbering scheme, red or blue? Blue. Okay. Okay, so when we assemble our name, we're going to indicate the location of that double bond with the lower number carbon. Okay, so what do I mean by that? If I look, I see that my double bond is located between carbons 1 and 2. So I'm going to refer to its position by the lower of those two numbers, right? By the 1. So this would be 1 pentene. Okay, I have the location of that double bond. And I have that ENE ending, letting me know that it's an alkene. And then, of course, my pent for my 5 carbons. What's up?
So in this case, the numbering structure would just go the closest to the double bond?
Yeah, so you're going to number, and again, you want the lowest number in your name, right? So that's why I picked the blue instead of when I numbered the other way. And then once you have your numbering scheme, you're going to refer to the position of that double bond by the lower of the two numbers. It's always going to be between 2 carbons, right? Whichever one's the lower number, that's how you indicate the position. Cool. All right, so let's just practice a few of these. So how many carbons do we have in our parent chain for this first example? 6. So my longest continuous set of carbons are these ones right here. Still got this other one unaccounted for off of my parent chain, so that would be a methyl group. I'm going to number my parent chain. All right, I want the lowest possible numbering in my name here, so I'm going to stick with the left to right. Okay. So now when I assemble my name, I'm going to indicate that I have 2-methyl. I have a methyl group on carbon 2. If this was an alkane, it would be just 2-methylhexane, but now I also have to indicate the position of that double bond. So 2-methyl-2-hexene. Okay, so we got 2 2's in the name. First is my substituent that goes out front, along with its location. The second 2 is indicating the position of what? The double bond. And notice that that goes right out front of that parent chain, my hexene. So this is the position of my alkene double bond. So 2-methyl-2-hexene. I got dashes separating the numbers and the letters. All right, and to be clear, this is all run together, all one word here.
I have a question.
Yeah.
Could you have gone like 1,1-dimethyl, 1-pentene?
No, so you're not doing your, you don't have your parent chain correctly found because there's a longer continuous set of carbons in there, right? You essentially started counting your parent chain at that second carbon and made this a methyl group as well. You want the longest continuous set of carbons.
What if we did just 2, 2, and then the methyl?
So the one has to be out front, that's your substituent location, and the other 2 is always, the location of the double bond is always going to sit right in front of that parent chain. All right, so this one's a little bit trickier. In particular, finding your parent chain. How many carbons are in our parent chain here?
4.
Cool. I think it's really tempting to say it's these 5 here because that's my longest continuous set of carbons. But remember the little twist we added on there. It's got to contain that double bond. So before I do anything, I know that these 2 carbons right here are in that parent chain, right? So then I'm just looking for the longest continuous set. It wouldn't matter which direction you went in this case. So now I have these 2 carbons unaccounted for. What would that be considered? An ethyl group. I can number left to right or right to left. Which one are we going to want to stick with? Red or blue?
Red.
Red, right? We want the lowest number in our name. Okay, so now when I put my name together, I'm going to put my substituent first, right? So that's that 2-ethyl. Now I'm going to put my parent chain, my location of my double bond, 1-butene. So 2-ethyl, 1-butene. All right, we got one more sort of rule to add to our numbering here. And let's take a look at this example. All right, so let's do our first steps together here. We got to find our parent chain. Everybody take a second, see if you can't find our parent chain. I got this substituent right here sticking off of that parent chain, what we call a fluoro group. All right, but now I'm going to put in my numbering. Okay, and this is where we're sort of going to complicate things here. Because previously you would want just the lowest number in your name, right? So you would look at the number of the fluoro group, and in this case now our double bond, but our functional groups have what is called priority, all right? So under our numbering here, we're going to make a note that our functional groups, aka that double bond, gets priority when you number. Okay, and what does this word priority mean? It means you ignore everything else in your molecule and you're only going to pay attention to the location of that double bond when assigning your numbering scheme. All right, so this is our first functional group. These functional groups in nomenclature are special. They have what's called priority. First of all, they have to be included in the parent chain. We sort of laid that out. But also with regard to our numbering, when you number your molecule here, the only thing you're going to pay attention to is the location of that double bond. I don't care where that fluoro group is. I don't care where my substituents are. I only care where my functional group is. So looking only at that functional group, which numbering scheme are we going to pick? Blue or red? Blue. Cool. Okay, so then you can take a second and finish naming this off. But again, by priority, when numbering, we mean we only pay attention to that functional group. So I'm still going to assemble my name the same way. I'm going to put my substituent out front. That's 6-fluoro 3-heptene. Cool. All right, and now for the worst of all of them. I'm kidding. That's it. So this is our sort of altering of our rules for nomenclature here. Now we've introduced a new functional group, okay? Importantly, it changes how we're going to find and name our parent chain. We're going to make sure that the functional group is in that parent chain, and we're going to update our ending. Now it's not an alkane with an ane ending, but an alkene with an ene ending, okay? Nothing different about how we find and name our substituents, but when it comes to our numbering, we also have this new concept of priority here. When there's a functional group in that molecule, and again, our double bond's our first functional group, it gets priority when we number our molecules. So we're going to only pay attention to the location of that double bond when numbering. Did you have a question?
I don't know if it's like we're going to learn about it more ahead, but so if there's a double bond in like the shape, we would just add cyclo in the front, right? Before the pentene.
Yeah, so yeah, and what we'll do so we're going to do a few more practice examples, but yes, we'll do a cyclic alkene as well. Okay. All right, so let's just name a few more here, make sure we got these rules down. All right, let's go through these first two, and then I'll give you some more time to work on this third one here, but I think it'll be more helpful to go over this second example first. Okay, so this one, again, we're going to find our parent chain. Importantly, my parent chain has to contain those 2 carbons about my double bond. So now we have these 2 substituents. One of them is a 1 carbon group up here, a methyl group. The other one is this 2 carbon group, so this would be an ethyl group. I'm going to number my parent chain, 1, 2, 3, 4, 5, 6. Go the other way, 1, 2, 3, 4, 5, 6. Okay, so the only thing I'm going to pay attention to is my double bond here. So which one am I going to pick based on that double bond, red or blue? Okay, we got a tie here, right? They're both between carbons 3 and 4. So how do we think we break our tie? Now we're going to look at the other substituents, right? The first thing we did is we blurred our eyes to anything else on this molecule and only focused on the location of that double bond. But regardless of whether I pick blue or red, that double bond is going to be located on carbon 3. So now I need to look at the other numbers in my naming here. If I picked blue, I would have my double bond on carbon 3, a methyl group on 2, and an ethyl group on 4. If I did my red numbering scheme, I have my double bond on 3, my ethyl group on 3, holy cow, and my methyl group on 5. Which one do we want to go with, red or blue? Blue. So we didn't even get to the alphabetical order yet, right? Because we didn't have a full-on tie with all of our numbering. We are still going to go to the lowest number in the name here. In this case, I was tied at my double bond, so I'm going to look at the position of everything else to make sure I have the lowest number in my name. So we're going to go with blue. When I put these together, my ethyl and my methyl, which one's going to come first in my name? Ethyl. So now when we assemble, we always assemble in alphabetical order. 3 ethyl, 2 methyl, 4 ethyl, 2 methyl. And now we have our parent chain, our 3 hexene. All right, so 4 ethyl, 2 methyl, 3 hexene. Beautiful name. Okay. All right, cool. So now we're going to go to these cyclic alkenes. How many carbons do we have in our parent chain? 5. Okay. Sort of the most important thing to note when you have your cyclic alkenes is the location of that double bond. We prioritize when we number, right? So what 2 carbons are that double bond going to be sitting between? 1 and 2. Always between 1 and 2, right? So then when I do my name, am I going to say 1 cyclopentene? Right? Just like we talked about before, if I move that double bond, is it going to change the location from being carbon 1? No. So just by saying cyclopentene, we know exactly where that double bond is located because it's always between carbons 1 and 2 in our ring, right? We prioritize it when we're numbering, so it's always going to be between carbons 1 and 2. Okay? So let's just make a note, and then you can take this, by analogy, do that third example there. What's up?
So if we were to put the 1, would it technically be wrong?
It is technically wrong, yes. It is a very minor mistake in the grand scheme of things, but nonetheless, it is considered to be wrong. So cyclopentene, our double bond is always between carbons 1 and 2. All right, cool. So with that in mind, take a second and do that last example. so my parent chain, or my 5 carbons in my ring. Okay. I have this methyl group, but I have to indicate where that methyl group is on this ring relative to that double bond, right? So again, my double bond's always between carbons 1 and 2. So I can either go from here 1, 2, 3, 4, 5, or we can go the other way 1, 2, 3, 4, 5. Which one do we want to pick? Red or blue? Red, right? We want to put that methyl group on the lowest possible number. There's no rule about clockwise or counterclockwise, right? These are 3-dimensional objects. You can pick it up and flip it over. Okay. So this would be 3-methyl, cyclopentene. Okay, again, I don't have to indicate where that double bond is because it's always between carbons 1 and 2, right? Whenever you have a ring, a cyclo and an ene, you always know the position of that double bond. So 3-methyl cyclopentene. Cool. All right, so last thing we're going to discuss with alkenes, and then next class we'll pick up with reactions of alkenes, is what's called stereochemistry. Okay, so we were first introduced to this idea of stereochemistry when we talked about our cyclic alkanes. Okay, remember the whole idea was that cyclic alkanes, because you've locked them in this ring, they can no longer freely rotate about those single bonds. So if we have, for example, 2 methyl groups that are pointed in the same direction away from that ring, they're locked in that direction, right? You're not going to be able to rotate so that one of them's pointing into the board and one of them's pointing out. They're both pointed out at you here. And this molecule is distinct from if we had one pointing into the board one pointing out and one pointing in. And we had fancy ways to distinguish between these 2 stereoisomers here. We called those the cis and the trans isomers. So everybody take a second and label these structures here. So in this case, they're 2 methyl groups. If those 2 methyl groups are pointed on the same side of that ring, whether they're both a wedge or both a dash, that's what we call the cis stereoisomer. All right, and if they're pointed in opposite directions, one's on a wedge and one's on a dash, that's what we call the trans stereoisomer. Okay, so these were cyclic alkanes. And again, the reason why we have this stereochemistry property is because they do not rotate. All right, so those 2 groups are stuck on that same side of the ring, for example. All right, well now let's look at double bonds, alkenes. All right, we got this same sort of concept of stereochemistry that's going to arise. And that's because double bonds also do not rotate. So if we took a look at 2 molecules of butene, 2-butene. Okay. Both of these molecules, if you were to name them, would be 2-butene. All right, I got my double bond between carbons 2 and 3 in this 4-carbon alkene. But these are two distinct molecules here. Okay, again, we would call these a pair of stereoisomers. Right, just like we saw above. And what makes these distinct molecules is that these two groups, these two carbons, are locked on their about that double bond. So in my first example, the one on the left, those two carbons are pointed in opposite directions about that double bond. In my other example, now they're pointed in the same direction about that double bond. And again, double bonds can't rotate, so it can't switch between these two conformations. It's locked in one or the other. So in the same way that we have cis and trans isomer for cyclic alkanes, we see the same thing for our alkenes as well. So this we would call the this one we would call the trans 2-butene, because those two groups are pointed on opposite sides of that double bond. And my other example here would be the cis 2-butene, because those two methyl groups are pointed on the same side of that double bond. Okay? So in the same way when we had our cyclic alkanes that couldn't rotate, we had these stereoisomers where these groups are locked in these particular conformations. We see the same thing for alkenes, depending on where these groups are about this double bond here. So for being good, let's go back up to this example here, our 6-fluoro-3-heptene. We were looking at a specific stereoisomer of this 6-fluoro-3-heptene. Everybody take a second and tell me if we're looking at the cis or the trans isomer of this here.
Cis.
All right, so we're looking at this double bond. Let me get rid of all of these little markings here so we're not too confused. All right, so now I'm specifically looking at my double bond and these two groups that are attached to that double bond. Are they pointed on the same side of that double bond or opposite sides of that double bond? They are on opposite sides. So this is the trans isomer of that 6-fluoro-3-heptene. For the sake of completeness, let's take a second and draw what the cis isomer would look like. What's up?
So whenever we went over alkenes, you said that if there aren't like dashes or like the solids,
Yeah.
that we don't know, does that not apply to alkenes?
Okay, so this is a very good question. I didn't use dashes and wedges down here, right? So what's up with that? Like I used dashes and wedges to represent our stereoisomers before. Here they're just all flat. So how am I supposed to be able to tell, right? Well, remember our alkene geometry is what we went over at the very beginning where all of these atoms lie in that same plane. So it would be incorrect to draw one on a wedge where it was pointed up or pointed down because they're all sitting flat here. So you just don't see the same dashes and wedges with alkenes that you see with alkanes. All right, so
It's not about the ones on the end, it's just about the ones at the beginning.
It's the ones about the double bond, right? Because this is like what I've highlighted here. This is the region of the molecule that's locked in place. All the single bonds are going to be flipping around, rotating like crazy. But this is locked. This is the one region of this molecule that is, it's not only stuck in this conformation, it's also perfectly flat right here as well, right? So these molecules from like a mental image standpoint just look a little bit different. But yes, I don't care about my fluoro group or anything like that. I only care about what's about that double bond. So then if I wanted to draw the cis conformation, it's going to look a little weird. I'm going to have to draw those bonds pointed in the same direction. So I'm going to draw that now pointed in the same direction as my other existing single bond. I got to make sure I have the correct number of carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So I'm missing one on the end here. Boom. So this would be our cis conformation of that same 6-fluoro-3-heptene molecule. They do, yes. Not very differently. They will share many of the same reactions, but if you took a beaker of one and a beaker of the other, you would see they have different boiling points and different freezing, like different physical properties altogether. They're going to be very similar compared to like a random other molecule, right? But nonetheless, they are completely distinct molecules. Yes, they have their own physical properties. Cool. Let's just practice this one more time here. And so within your 3 examples here, 2 of them represent a pair of stereoisomers. So take a second and circle the pair of stereoisomers that you have. All right, so let's do this first one here. 1, 2, 3, 4, 5, 6. And that double bond is located between carbons 3 and 4. So this would be 3-hexene. But if I look down here, this is also a 6-carbon parent chain. 1, 2, 3, 4, 5, 6. And again, that double bond is located between carbons 3 and 4. So this is also 3-hexene. All right, so the difference between these is the stereochemistry of that double bond. What's this first one, the cis or the trans isomer? Trans. So the trans one is kind of like the normal zigzaggy line that we're used to seeing, right? The cis isomer is always going to look like it has this weird kink in the middle there. So this would be the trans 3-hexene. This would be the cis 3-hexene. All right, and again, this is a pair of stereoisomers. All right, so let's do this one real quick. 1, 2, 3, 4, 5 carbons in that parent chain. And then I have this methyl group on top. I'm going to number my parent chain 1, 2, 3, 4, 5. Or 1, 2, 3, 4, 5. Which one of these numbering schemes am I going to pick? Blue. I want my double bond to be at the lowest possible number. Okay. I'm going to get rid of my markings here to make a point. Okay, so putting it all together, this would be 2-methyl 2-pentene. But now we discuss this stereoisomer business, cis or trans. Which isomer are we looking at here? All right, cis, trans, or trick question? This is a trick question, okay? So this particular alkene does not have any stereoisomers because if I swapped these 2 groups right here, I would get the exact same molecule, right? So how can we tell when an alkene does not have any stereochemistry? You will always have 2 identical groups. In this case, these 2 1-carbon groups on at least one of your double bond carbons. Okay, so there's some alkenes that just don't have stereochemistry because of the symmetry, right? A stereochemistry is all about the fact that this double bond can't rotate. Well, if I swap those 2 groups and I have the same molecule, I don't have any stereochemistry to worry about, okay? If we look at our previous examples, I was always pretty careful to not choose examples that had stereochemistry. So if we look at these 2 here, again, we have this same situation where on one side of my double bond are 2 1-carbon groups. That molecule doesn't have any stereochemistry. If we look over here, this molecule definitely doesn't have any stereochemistry. These are both the same. But also on this carbon, what do I have on bound to that carbon? 2 hydrogens, right? So 2 identical groups there. So this double bond doesn't have any stereochemistry either. Okay? Same thing up here. 1-pentene. How can I see that this doesn't have any stereochemistry? Again, on this end carbon here are two identical groups, two hydrogens. Okay? So, if they're both the same, you can't be assigning any sort of higher or lower or anything like that. So, yes, these molecules don't have any sort of stereochemistry associated with them. Cool.
That molecule would just be 2-methyl, 2-pentane.
You're done there, yep. That's it. There's no indication out front of cis or trans because, again, this molecule doesn't have any stereochemistry. There's only one way to draw 2-methyl, 2-pentene. Cool. All right, we're going to call it there. That seems like enough for today. All right, next class we'll start talking about reactions of alkenes. Alkenes always follow a similar pattern for their reactions.